Last topic in our study of advanced solutions is boiling point elevation and freezing point depression. These are colligative properties and are treated similarly. They're colligative properties, as you'll recall, because the type of solute particles that we add to the solution to cause the boiling point elevation and freezing point depression will not have an impact on the change in temperature. It is simply the number of moles of the substance of our solute that will affect the elevation or depression. The amount of boiling point elevation and freezing point depression that is experienced is directly proportional to the amount of moles of solute ions. Now, when we look at boiling point elevation, what this means is that if we have pure water compared to a solution where we've dissolved something into the water, the solution will have a higher boiling point. We experience this when we're cooking pasta. We're told that we should add salt to our water when we are going to cook pasta. And there's a common myth that it actually makes the water boil faster by adding the salt, but that's actually an incorrect statement. The truth is that the water will boil at a higher temperature, so it will take longer to boil the water. However, because we are boiling it to a higher temperature, the pasta will take less time to cook. A simple application of freezing point depression is how we salt our roads. When we have pure water compared to a solution where we've got a solute dissolved, the solution will actually have a lower temperature of freezing. And so this is why we salt the roads. By salting the roads, we allow the water on the roads to stay a liquid at lower temperatures. Now, a very important thing to remember is that ionic particles and molecular compounds will behave differently. They'll dissociate differently in water, and therefore the freezing point will and boiling point will elevate and depress differently. So we need to consider the number of solute particles that are put into the solution. Something like sugar, which is molecular, goes into solution in a 1-to-1 ratio, whereas sodium chloride will put 2 ions into the solution. When we look at a phase diagram, okay, the solid line here is our normal phase diagram, and the dashed line is showing us the impact of a solution. Okay, so this dashed line represents the changes that occur because we've got a solution rather than a pure liquid. So what we're seeing here at this end, going from a liquid to a vapor, what we are seeing is the normal boiling point, which occurs at 1 atmosphere, and then the boiling point of the solution. And as you can see, the boiling point is elevated. Okay? And this difference here is called the change in boiling point, or delta TB. At this end of the diagram, where we're looking at the phase change from liquid to a solid or freezing, you can see that the solution has a lower freezing point than that of the pure liquid. Okay, so this is the normal freezing point at 1 atmosphere, and this is the freezing point of the solution. The difference here is delta TF, or the change in the freezing point. Now, this is the equation that we use to monitor the boiling point elevation, and there's a similar formula for monitoring the freezing point. This is the boiling point elevation, so this is the increase that we'll experience on the boiling point. I is the number of solute particles, okay, per unit of solute that we have. So something that is molecular will have an I value of 1. Something that is ionic with 2 ions put into solution will have an I of 2. So something like sodium chloride will have an I value of 2. Something like calcium chloride, or CaCl2, will have an I value of 3. It's called the Hoff factor. This constant, Kb, is the molal boiling point elevation constant. And this is a constant that's related to the solvent. Okay, so the solvent itself will have its own constant associated with how a solute affects its boiling point. There is a table in your note at the bottom of page 9 that shows you the molar boiling point and freezing point depression constants for several common liquids. So you'll see for water, the boiling point constant is 0.52 degrees per molar of solute added. So the number of solute particles is what affects the boiling point directly. So we are going to use molality to give us an indication of the amount of solute that's actually in the solution. The reason we use molality in this formula is because it does not change with temperature. If we were to use molarity, although it would give us the moles of solute in the solution, it would not be independent of temperature. So we need to use molality. Okay, so for the freezing point depression, we've got a similar formula. The freezing point depression is equal to the Van 't Hoff factor times the molar freezing point constant for the solvent times the molality. Okay, the key here is that the constant that we use, the Kf or the Kb that we use in these formulas, is related to the solvent. And the molality is giving us the indication of the solute, and the I is related to the solute. Now the I value, the Van 't Hoff factor, is something that we're going to use a calculated value for when we're doing calculations. So it's simply based on the number of ions that we predict will be in the solution. So anything that's molecular, like sucrose, will have an I value calculated at 1. Anything that is ionic, we need to break it up into its ions and count the number of ions that will be in the solution. So something like HCl will have 2, NaCl 2, magnesium sulfate, which is Mg2 plus and SO4 2 minus, will also have 2. Magnesium chloride and iron chloride have 3 and 4 respectively. Now these values here, these measured values, are important to discuss. You'll notice that when we measure the actual I value, it's a little bit lower than what is expected by the calculated value. The reason for that is when we have ions in solution, they form what are called ion pairs. So although when we think of something like hydrochloric acid as dissolving in water and breaking up completely into H plus and Cl minus, it is possible in that solution that a cation and an anion will be attracted to one another and form what's called an ion pair. And so rather than them acting as 2 solute particles in the solution, they're only going to act as 1. Now you'll notice for different ones, there's a different impact. So for NaCl and HCl, okay, which both consist of a positive and negative ion, their measured I values are 1.9. Meanwhile, for MgSO4, even though we predict it to have the same I value, it has a significantly lower measured I value. The reason for that is related to the charges. So because magnesium and sulfate have a greater charge, so a 2 positive and a 2 negative, they're going to form significantly more ion pairs in the solution. What we need to be able to do are there are 2 types of calculations. We need to be able to calculate the melting point and boiling point of different solutions. And we're also going to need to use freezing point depression and boiling point elevation in order to calculate the molar mass of an unknown compound. Let's start with the first type, calculating a melting point or a boiling point. In this example, a solution was prepared by dissolving 18 grams of glucose in 150 grams of water. First, it asks us for the molality. As you know, the molality is the moles of solute per kilogram of solvent. So what we need to do is calculate the moles of the glucose. The molar mass of the glucose is 180.18. So the moles is equal to 18 divided by 180.18. So we've got 0.0999 moles. The molality is therefore 0.0999 moles divided by 0.150 kilograms of water. So we've got a molality of our solution of 0.666 molal. To find the melting point of the solution, we need to find the freezing point depression that is caused by this solution. So we're going to use the relationship delta TF is equal to I KF M. I in this case, because we're dealing with glucose, which is molecular, is 1. The solvent that we're dealing with here is water, and the freezing point constant for water is 1.86. The molality of the solution is 0.66. So as you can see from this equation, the change in temperature is dependent on the solvent and on the amount of solute that's dissolved. So the freezing point depression here is 1.23 degrees Celsius. So what that means, if we want to know what the actual freezing point is, our freezing point of normal water, pure liquid water, is 0, and we are depressing it by 1.23. So the new freezing point of the water is 1.23 degrees Celsius. Okay, so we're going to look at another example here, and I'm going to make a change to make it more realistic. Okay, we're going to use 51 grams of ethylene glycol, and this should be solute here. Okay, so we're going to calculate the freezing point and boiling point of a radiator solution containing 51 grams of ethylene glycol in 200 grams of water. And it gives us the molar mass, and it reminds us, which we can get from the tables, but this should be 0.52. So these are the freezing point and boiling point constants for water. It's 1.86 for the freezing point constant and 0.52 for the boiling point constant. So we need the molality of the solution. The molality is going to be the moles divided by the kilograms of solvent. So the moles we have by taking 51 divided by 62 is 0.822. The kilograms of solution of solvent that we have is 0.2, so we've got 4.11 moles per kilogram, okay, or molal. So we can find the boiling point elevation here. Ethylene glycol, being molecular, has an Van't Hoff factor of 1 times 0.52 times 4.11. Okay, so we're going to have 2.13 degrees Celsius elevation. So the new boiling point is elevated from the normal boiling point of 100. So it's 102.13. For our freezing point depression, the Van't Hoff factor is 1. The constant is 1.86 times 4.11. And we get 7.64, so our new freezing point is negative 7.64 degrees Celsius. Okay, and this is appropriate for a radiator solution because we need for it not to freeze when the engine is cold or to boil when the engine is hot. In this next example, I'll allow you to do it yourself and check your answers with me. Before we do that, we'll just discuss a few points here. First of all, urea, the formula for it is NH22CO. The molar mass is 60.06. Now the difference between these two solutions, in the first one we've got sodium chloride dissolved, and in the second one we've got urea dissolved. So what's going to happen is the I value in sodium chloride is calculated at 2, and the I value for urea is calculated at 1. So you're going to use the calculated values. You don't use the measured values from the table I previously showed you. Okay, that was more for a point of discussion. Okay. So you'll find the molality of the given solutions, and then you can find the freezing point depression and boiling point elevation. And we're dealing with solutions prepared with water, so you're looking at a change of elevation from 100 degrees Celsius for the boiling point and a depression from 0 degrees Celsius for the freezing point. In this example here at the bottom, okay, it's a multiple choice question with multiple parts. So we want to know out of these substances listed which one is going to have the higher boiling point, the higher freezing point, and the highest vapor pressure. What we have to remember is that these are colligative properties, and so their changes depend on the amount of solute in the solution. We must remember that the more solute, the higher the boiling point, the lower the freezing point, and the lower the vapor pressure. So when we look at these substances, we need to decide which one of them is going to put the most number of ions in solution and the fewest number of ions in solution. Okay, glucose is going to have an I value of 1 because it's molecular. The next three are all going to have I values of 2 because they've got 2 ions in them. Knowing your polyatomic ions is critical for this. And the last one is going to have an I value of 3. Now it's important to note that we're comparing solutions of the same molality. If you were to compare solutions of different molalities, you would need to take into account the combined impact of the molality and the I value to see what the overall change would be on the boiling point, freezing point, or vapor pressure. So the highest boiling point is going to be E because boiling point is elevated greater for greater number of particles. The highest freezing point is going to be A because, as you know, freezing point is depressed, so this one will have the smallest amount of depression and therefore will have the highest freezing point. For the lowest vapor pressure, more particles equals lower vapor pressure, so therefore E is also the answer for that one. We have one more type of problem to look at, and that is using colligative properties to find the molar mass of a substance. Finding the molar mass of the substance can help us to predict the molecular formula of a compound. So in this example, a 5.5 gram sample of an unknown compound with empirical formula C3H3O was dissolved in 250 grams of benzene. The freezing point of the solution is exactly 1.02 less than pure benzene. Determine the molar mass and the formula of the compound. So we are given the freezing point constant for benzene, which is our solvent, and we are given the freezing point depression of 1.02. So we know delta TF is equal to I KFM. And knowing the freezing point depression is 1.02, knowing the I value for the molecular compound is 1, and the freezing point constant is 5.12, we can determine the molality of the solution that was prepared. So the molality of the solution that was prepared was 0.1992 moles per kilogram. We know that the mass of the solvent used to prepare this solution was 250 grams, so we can determine the moles of the solute simply by taking the molality and multiplying by the mass of the solvent, which is 0.25. So we know that we've got 0.0498 moles of solute in this solution. We can therefore calculate the molar mass, which is the grams per mole. So we've got 5.50 grams of the solute, and the number of moles of solute was 0.0498. So this gives us a molar mass of 110.43 grams per mole. The second part of the question is to determine the formula of the compound. This is a grade 11 topic. You've got the empirical formula of the compound, which, as you know, gives the simplest ratio. Its molar mass is 55. So by comparing the molar mass of the molecular compound to the empirical compound, simply by dividing, so 110 divided by 55, we can see that the molecule is double the empirical formula. So the formula is C6H6O2. And that concludes our study of advanced solutions.